card works. They can store data if they're a little bit more powerful. They can store, like, you know, your hotel room key card can be programmed with your hotel room. Or the really nice ones, meaning the ones that don't cost 1 cent, can actually do crypto. And they can communicate back and forth using some kind of protocol over, you know, some radio frequency kind of transceiver. And so you've seen a bunch of these things. I don't know if any of you have cars and you have EasyPass. EasyPass is kind of an upmarket version of what these little tiny things are. So the big application people are deploying these for, besides product cards, is product inventory management. They're going to put RFID chips on every product you buy, and then all of a sudden, just, you know, finding out what's in your store is a question of waving a wand through the aisle. You know everything on the shelf. Someday, checking out of a store is going to be a question of just pushing your shopping cart through a reader, and it will scan everything, and that'll be great. The upmarket versions of this are actually more sophisticated. EasyPass has a battery, and the battery allows it to broadcast at a larger range, at a higher baud rate, basically, a higher BPS. Why do you need that for something like EasyPass? Yeah?
Because you're going really fast, and you don't want to drive close to a sensor on the car.
Good. You want to drive 70 miles an hour past something, you know, some toll booth, and you want to have this, all of your data get basically blasted out. And so there's a computer inside of here, there's a battery, and there's a big antenna. And this is a reader over here on the right side. So RFID does all of these different things. Okay? So the old school, the cheap RFID tags, we call them Walmart RFID tags, they're pretty dumb. You send a signal, usually it's passive, so you send power and some activation signal to them, and then they broadcast back an identifier, which is fixed and built into them. It's actually a little more complicated than this. There's a collision avoidance protocol where they try not to talk over each other. So if you're scanning a whole pallet full of shampoo bottles or something, you're not going to get like a bunch of collisions. But this is all done, and you get back something. So what's really interesting about these RFID tags is, you know, even though we did this research several years ago, these devices are not getting smarter. They're not getting smarter because this is kind of a neat application of Moore's Law. We think of Moore's Law as basically doubling the capability, roughly speaking, of our computer chips every 18 months. But the other way Moore's Law can work is they can make stuff cheaper. So Walmart tags were about 50 cents when we started this research. Now they're under 5 cents. They're probably down, like in some cases, down to less than a penny. When they get down to a small enough value, they're going to be on everything you carry, and that'll make it really easy to track all sorts of stuff. Okay, so this is interesting, but the problem is, because the goal is to make these extremely cheap, nobody is bothering to put privacy or security protections in them. Which means when you buy clothes and they have RFID tags in the collar and you walk around, technically speaking, somebody with the right kind of antenna could track you by looking at those unique identifiers. Yes?
So, for example, I have a credit card which has metal, and I've noticed that is unable for my RFID tag-based items in close proximity to it. For example, I have to remove my credit card from my wallet in order to use it until it's yours. Are there other issues with consumers carrying objects that would block that, basically?
There are a lot of things. You can actually go to like Eastern Mountain Sports. You can buy a wallet that is lined with like tinfoil, and the idea is that it prevents these credit cards allegedly from being stolen or stuff like that. But yeah, lots of things block these. Tinfoil works really well if you want to block something. You don't have to pay Eastern Mountain Sports or whatever it is. The passports nowadays, U.S. passports, have a chip inside of them. And people were very freaked out because you're traveling through some maybe dangerous country and people can figure out somehow automatically that you're a U.S. citizen. Like they can't figure that out anyway, but whatever. So, you know, people are really freaked out about this because there's this kind of tracking privacy issue. But these are privacy issues, and one could say that privacy is different than security. So maybe we don't care about privacy for the moment. Let's think about security. So privacy means tracking. Of course, you can track things if they're in your clothes and your passport and so on. There's a foil container. There's a little icon, probably on the front if you have a U.S. passport, that looks like a chip. It's not actually the chip, but it indicates that you have an RFID device inside your passport. This guy over here on the left actually installed an RFID device into his hand for reasons I don't fully understand. But he did this, I don't know, to make a point about something. And medicine bottles have these a lot of the time, so it's really easy to track, do inventory management and stuff. But that, you know, if you're carrying around a bunch of medicine, you have a condition that you don't want people to know about, that could be a problem. Yeah?
How is this different than just pure barcode?
So the difference is mostly two things. One is distance. So some of these devices can be read from a distance of several meters away. So with a barcode, I've got a barcode in my backpack. I'm pretty safe. Nobody's going to track that, unless it's on, you know, my clothes or something like that. But with these devices, I've got an RFID chip in my backpack. I can walk through a gate or, you know, into a store, and it can be instantly scanned, and everything else in my backpack can be too. So there's kind of just a difference in terms of ease of scanning and tracking. That's mostly it. And theoretically, the distance could be extended to maybe dozens of meters, but it takes really big antennae. It's not super easy. Okay, so there's this question about tracking. People were really freaked out about it. I don't think they've gotten any reassurance, but it's still kind of something that's on people's minds. Okay, there's another question though. If you're using these devices, what about security critical applications? Okay, so these are actually being used for lots of stuff. You guys mentioned credit cards. Of course, they're being used for payments. I showed you Easy Pass. They're being used for toll collection. So if you could break the security of these systems, you can presumably drive around for free. And the really interesting thing I think I mentioned earlier in this class is vehicle anti-theft systems. Okay, and I think I told you this way back when, but just to remind you, back in the olden days, if you watch a movie from the 70s, every crime movie from the 70s has somebody hotwire a car. And it involves taking a screwdriver, popping a plate off, and touching two wires together. You can't do that today. You can't do that. Even if you can get past the mechanical locks, you can't do that because, of course, modern cars are just big computers. And the engine computer, the engine control unit, has a computer that controls the fuel injection, and it refuses to start unless it gets some kind of confirmation. And the way it gets confirmation is that in the head of your car key, there's a little chip. It's very hard to see, but there's a couple different form factors. And these little chips are RFID chips. They're usually powered by a signal that comes from the steering column of your car. They get communicated with, they do some kind of protocol, and at the end of this, the ECU knows not only did you turn the key or press the button, but actually it is in the presence of an authentic car key. And then modern, super great ones like these guys actually have a distance of a meter or two, so you don't even have to actually put a key into the car. Okay, all cars have this. Insurance companies mandate it, and they've resulted in this vast reduction in theft because it used to be really easy to steal cars, and now allegedly it's impossible. Well, that's the question. Is it really impossible? Okay. So I told you this, so I think I even showed you an example of a vehicle immobilizer, but vehicle immobilizers look like this. You have got a key and you've got a steering column, and the older designs really sucked, and I think we had a demonstration the first lecture where what would happen is there's a shared ID number that both sides would have, and the car steering wheel would say query, and the ID number would be fixed, and that kind of sucked for obvious reasons because anybody who got hold of your key could clone your key and then steal your car. And this actually started happening. Valets started stealing cars, and the mafia got involved in this. And so, of course, the next generation uses, yeah, I can skip this. The next generation of these things actually do something clever. I can skip all this stuff. Oh, sorry, I can't. Anyway, so it's very easy to do something where you scan somebody's key and you go on. I'll show you the fix of this a little bit later. Okay, so you can just replay copied responses from anyone's key, and you can steal their car. Okay, so this is where we get into what we actually started looking at. Okay, so the project outline, what we wanted to do was we wanted to look at a few widely deployed platforms. So we got some money from RSA Security at the time, and they said, look, we're interested in RFID. We want to know if this is good. Let's see if we can look at a few platforms that people are using for these applications. Let's try to reverse engineer them, figure out how they work, and that means kind of overcoming all these kind of crappy physical limitations. And then we can actually see if they even bothered to put security or if they're just a joke. And then we have to kind of figure out how to break them. The problem is we were a bunch of computer science students, and we didn't know anything about radios. We really didn't want to learn anything about radios because we wanted to be computer scientists. So we had to kind of figure out how to do this all on the cheap. We picked a couple of targets, and one was this thing called the ExxonMobil Speed Pass. Any of your parents have an ExxonMobil Speed Pass? Good, yeah, my dad loves this. I don't know why, he's the only person I know who uses it. It's a little thing you put on your keychain. It's basically a payment device. You can go to an Exxon station, wave it by the thing, and you pay for gas. And you can also buy munchies, as I will show you a little later in the convenience store. So it's great. It only works at Exxon, but it has some kind of RFID chip in it. It's contactless and whatever. We wanted to look at that. And we also wanted to look at Easy Pass, which is, like I said, a toll payment system. Happens to be still pretty widely used. We had no idea how it works. And so we figured we'd look at Easy Pass first because it looked cooler. It was bigger. We could take it apart. Okay, so Easy Pass is a high-speed toll collection system. It's all over the east coast of the United States. There's pretty significant amounts of money. It costs about $20 to drive to New York. It costs a lot more if you go farther, longer distances. So a lot of people are spending a lot of money on this thing. The neat thing about this protocol, or this system, is like we discussed, it has a very large read distance. You can read it at dozens or hundreds of meters away while you're driving very fast. The problem with this, from a security researcher point of view, is that all of the details of this stuff are not public. It's a proprietary system owned by a bunch of different state governments. They're not sharing the details of their protocol or how any of it works. So if you want to figure it out, you kind of have to start from scratch. So how do you start from scratch? Well, First, you find some documentation online. There's a little bit of stuff. We found this really awful picture. Basically, it shows that there are these fixed readers, which I think you could have guessed if you've ever gone through a toll booth, that scan your EasyPass. They're at the top of the toll booths. The signal's read at highway speeds, and within the booths, the range is very limited, but it can be 100 plus feet. So we found this documentation that tells us just this much detail. From there, we needed to take apart an EasyPass. So we took apart this one. This is a Pennsylvania Turnpike EasyPass. We drove over it with a pickup truck. We took the parts and we opened it up. And what we found is this. So it's basically just this one pretty simple logic board. I'll give you a blown up picture of it. I'll come back to the details here. Let's see if I can. There we go. Here's the anatomy. So the real brains of this thing is a single control chip up in the bottom, top right. There's a big battery because it has to last for several years. We found that there were some receiver and transmitter circuits right here, filters down here, some receiver stuff. The transmitter is this big blob here, and then you can kind of see the antenna. This is what actually drives the signal. So that's the entire guts of an EasyPass. And we were also able to figure out, just by doing some simple analysis with an oscilloscope, that the frequency it operates on is about the 915, 914 megahertz range. Why is that a special frequency range?
It's pretty similar to cell phones, isn't it?
It's nearby, actually very similar to Wi-Fi. Why is that frequency range privileged and special? Why do so many devices use it?
That's like Wi-Fi. Is it Wi-Fi 2.4?
It's actually the original Wi-Fi, because 2.4 uses 2.4 gigahertz. But the original Wi-Fi was in the 900 megahertz-ish range. What's special about 900 megahertz? The unlicensed frequency band. You can use it for whatever you want, and this is what they chose to use it for. It's EasyPass. Great. Data transmit rate's really high. It can send half a gigabit per second. Doesn't actually send very much data. It just goes chirp, chirp, here's my serial number. But it has to do it quickly because in the time it takes to go, in 1 second, your car can go quite a big distance if you're traveling at highway speed. So it has to speak very quickly. Okay, so we were able to look at this thing. Okay, so we had some problems. The first problem we had is that even though we had a tag and we'd taken it apart, we could not get it to talk to us in the lab. And the reason is the tags don't speak. They sit there and they preserve their battery until you go through a toll booth. And so we needed some kind of signal to make the thing talk, but we didn't have a toll booth. Fortunately, there are a lot of toll booths nearby. You can drive down to the Harbor Tunnel, or you can go up to I-95 and you can actually get someone to scan your thing. Problem is you need a portable unit, a portable rig in order to scan, to actually monitor these signals that you can take in the car with you when you do this kind of thing. So we developed one. Okay, we have this crazy system. So the first part of our system, we all did this on the whiteboard, we would have an antenna, and we put this into a radio transverter, and that would go into something called a software tunable radio, which we spent a bunch of RSA's money on. Software tunable radio basically just tunes a particular frequency of the radio and then digitizes the resulting signal, and that goes into this analog digital converter board, and then we would just get bits, and then we're computer scientists, we can handle bits. From there we were good. So we figured we'd build this system, and then we talked to a guy who was actually an electrical engineer, and he told us we were being idiots. He said, don't build this whole system. You've got an antenna already. You've got all of the filtering circuits here on this board. All you need to do is put 2 jumpers into the right wires of this existing EasyPass that you already drove a truck over. And what you can do is you can plug those directly into your ADC board, and you can just get the data from those wires, which is smart. We were pretty dumb. And so we built the system. We called it the Frankenpass. I'll show you a picture of it. There you go. So there's the Frankenpass in operation down here. Sorry, it's not the best picture. But you can see somebody holding it. There's a wire with 2 things soldered to it. And it's in a car. This is actually the Fort McHenry Tunnel. And we got this little shuttle box PC that had a PCI slot, and we put a thing into it. So now we were good to go. We also bought a really big battery to power this all. We were set. Okay, so we did a field test. We drove down to the Fort McHenry toll booths down in Baltimore Harbor. And this is like a kind of a 1 or 2 mile long tunnel. Maybe you guys have been down there. You drive down there, and then you get to the first exit past the tunnel, which is like a big bunch of piles of dirt. And like we had to do this like 5 times. And this was, a few years after 9/11, so we were a little freaked out that we were going to get arrested or something, or maybe wind up like buried in those piles of dirt. It's kind of hard to say. So we were totally freaked out. But we did this, and we did a bunch of passes through the toll booths with our EasyPass talking presumably to the thing. And we brought all our stuff and we did it. And finally, when we went back and we looked at what we'd recorded, we found this. And from all of this data we were able to record, we could reverse engineer what is a very simple and unfortunately very boring protocol. It starts with the toll booth sending basically an activation pulse, just a 20 microsecond activation pulse at the right frequency. And when this EasyPass hears that activation pulse, it responds with a 516 microsecond response, which consists of, we were able to decode it, 256 bits, plus what we think is a CRC. And it's all Manchester encoded. So you can literally just read the bits off of this transcript and you can see what the thing said. Not very interesting. It looked like it was just sending a serial number, which means that basically there is no security built into these things. You can scan anyone, if you know the right pulse, you can scan an entire parking lot full of cars, and you can basically get the serial number of all their EasyPasses. So there's a tracking problem, but not really a really interesting security problem. We also found, after some more experiments, that there were parts of the response that did change. And we didn't actually figure out how to change them, but our theory, our hypothesis, is that there is an optional write phase where a toll booth can write data to your EasyPass, and your EasyPass will regurgitate it later. Why would that exist? What is the motivation for having toll booths write data into your EasyPass? Hang on, let me see. Anyone else?
Your balance.
What's that?
Your balance on your pass.
It could be, but then that would seem like a really big security problem, right? Because I could just like up my balance and be always, never pay for EasyPass again. Anyone else? Well, yeah, you answered a lot, so I'm just trying. Yes.
Can you tracking the traffic of where people tend to go?
That's possible, but they have a back-end database behind this stuff, so presumably they could do it that way. So if there's a back-end database, why do you need to write data into it?
If you wanted to remotely cancel one of these devices?
Maybe. I don't think that would work. Maybe it would work, but I don't think they were doing that.
Not sure if toll roads do this on the East Coast, but some places they'll do it where you only pay when you get off at an exit.
New Jersey Turnpike.
They do that on the
Yes.
Turnpike? Okay,
You
cool.
get on at an exit. In the old days, you get a ticket, and then you pay when you get off. In the modern system, you get on with your EasyPass, and you think since it's all connected to a big back-end database, it would write, entered on this exit, and then when you get off, it would say exited on this exit and calculate. But it turns out that the back-end database isn't very fast. And so they wanted a way to very quickly, and maybe not accurately, but very quickly calculate what your toll was so they could show it to you when you got off the interstate. And so what they do is when you get on the interstate, the toll booth writes which exit you get on, and then when you get off, your EasyPass regurgitates that information, and so that the exit toll booth can quickly say, oh, that'll be $8.38. I hope, we never verified this, I hope, for EasyPass's sake, that they actually do check the data from the database as a secondary check. They might not. So it might be possible, if you know how to use this protocol, to actually exit every time you go on the New Jersey Turnpike for essentially free. But I'm not sure if that's the case. Don't do it, you'd probably get arrested. So be careful. Okay, so if you want to attack EasyPass, is it very interesting? Well, there's plenty of power in this, which means you could read it from very far away. That's great, because it has battery. But there's no security in the tag at all, which ironically seems really bad. But from a security researcher's point of view, that's boring. It means there's not much work to actually do. And unfortunately, the EasyPass people have an answer to this, which is, well, if we detect somebody defrauding customers, we have a camera in the toll booth anyway. And so we're going to take a picture of them. And the fact that they can hack a protocol, they steal somebody else's money, we're going to find that person. I don't know if that's an accurate statement, but they feel that these toll booth cameras give them enough security anyway. So there's not really any interesting fraud that you can do against EasyPass. There is no protection whatsoever against tracking people. You could, if you were unethical, put a transceiver by I-95, and chances are nobody would detect it was there, and you could basically get the EasyPass identifier of every car that drives down it. You could put it outside the exit or the entrance to the NSA, and then you would have the identifier of every NSA employee that was going on and off that exit. And so there is really a tracking thing that people should be aware of. But again, it's not terribly useful for us. And the reason it wasn't useful for us is that in order to actually track a bunch of people and test these attacks, we would need to massively exceed the FCC's limit on how powerful your broadcast transmissions are. Now, if we were criminals, that wouldn't bother me at all, but we didn't want to break any laws as security researchers, so we weren't able to do it, and we didn't do much. Okay, so you could eavesdrop on a real toll booth and actually kept the responses. But mostly, EasyPass was kind of a bust, so we kind of left it there. The next target we looked at was this thing called the Texas Instruments DST. And the reason I mentioned this Texas Instruments DST, which stands for Digital Signature Transponder, even though there's no digital signature, is because we found after we cracked open one of these speed pass things, we found that the chip inside was a Texas Instruments DST. And that's what we were trying to target. But pretty quickly after that, we learned that Texas Instruments DSTs are also the chip that's used in about half of the world's vehicle immobilizer systems. So particularly Ford was a big one. I think Lincoln Mercury, a lot of Toyota cars use this chip inside of the head of the key to keep people from stealing cars. So here we have something that's actually really widely used and we hope has some crypto in it. This thing comes in lots of form factors. I don't have a really great picture of it, but there's this tiny little one that goes into keys. There's a slightly bigger one that goes into these speed passes. There's a really big one like this big. We couldn't figure out what it was for. And then we saw that somebody had a picture of a cow swallowing it. So apparently you can put these into a cow, and then you can track your cows with some kind of antenna. It was very weird. We gave no further
There's an obvious problem with that, which is that what goes in must come out.
I think it somehow lodges. I don't want to know.
Could you also just tag them with like something else? You know,
Yes, but then you
outside the cow?
apparently you make the cow.
Why not just chip them like you do pets?
I don't know.
Sorry,
I
didn't mean
I
to-
don't know anything about cows, and I don't want to learn. Although I did grow up in Vermont, so I should know more. Okay, so the Texas Instruments DST is actually a very different chip than the EasyPass. Okay, well, the first thing you notice, it has a much lower operating frequency. It's way down at 134 kilohertz, which has implications for its bit rate and has implications for lots of stuff. Again, this one is not a powered tag. It's passive, meaning you have to provide power from a distance. That's good because it hugely reduces the read range. It's no longer 100 meters or whatever. It's down to about a foot. So a foot's much easier. Okay, it's a challenge response protocol. And this is nice. So from a security perspective, we actually have some stuff going on. That's great. It's a 40-bit challenge that gets sent by the reader. There is a 40-bit key built into the chip and also in the reader. And then the reader somehow does some kind of computation and spits out a 24-bit response. That seems good. Why, when you just look at that data, what concerns you without knowing anything about the algorithms?
Those aren't big numbers.
Those aren't big numbers. Why not?
Because like 24 bits is, 40 bits is brute forceable. DES is 56 and it can be brute force.
Okay, so let's forget about that 40-bit key. This is a 24-bit response. What attack? If you don't know anything about the algorithms, and let's say you can't brute force the key, what could you do with a 24-bit response? What is
That's 3 separate characters. You could brute force that in seconds.
But remember, each time the reader scans you, it sends a challenge, and you have to come up with the right 24-bit response for that challenge. So what is your probability of success?
Low.
Low, right? 1 over 2 to the 24. So that's not very high. Seems like a pretty good thing, yeah.
You could map out the challenges and the expected responses because there's not that many expected responses.
Okay, so you could look for what's basically a collision on a challenge. What's the probability you'd see 2 of the same challenges in a session? I mean, you'd have to be watching somebody as they were trying to get into their car for like days and days. So this is probably, I mean, it seems sort of impractical just to guess a 24-bit response. So let's go with 24 being sort of okay. But you mentioned 40-bit key. You said DES isn't very great. Well, 40-bit keys are not great. So immediately, we know that this 40-bit key is going to be a problem. Does that mean we're done? Is this whole thing broken? Maybe, maybe not. I'll show you the protocol, which is really obvious. 40-bit key goes into both. There's a challenge, response equals Y. And so the question is, what's actually happening inside of this? We found a little documentation, and it says, okay, here's the reader. Reader sends a 40-bit challenge. The 40-bit challenge and the 40-bit key go into this. Well, what is this? It's an algorithm. We have no idea what the algorithm is. In fact, it turns out that this algorithm is secret. We have no idea what it is. So crap, how do you brute force a 40-bit key? We know we could brute force a 40-bit key. If this was in cipher, we knew how to actually write. What do we do when you have a secret algorithm? Is there some technique we can use? Sure.
Black box it, just throw inputs at it and...
It's a really good point. So have there been examples? People have tried to black box reverse engineer protocols. There was an old Japanese cipher machine called Purple, or the code name was Purple. It was, had its own, actually had a name in Japan. But that machine was basically black box reverse engineered by US military intelligence just by looking at inputs and outputs. But it's relatively rare for people to black box reverse engineer algorithms by just sending inputs and outputs to them. It doesn't happen very often. But presumably we could do it. We could definitely try to figure it out. The first thing you do is you look through the documents, you try to figure out if there's any information you can find that will help you. Okay, so unfortunately the actual cipher is available only if you sign an NDA with Texas Instruments, which we did not want to do because that would prevent us from publishing anything about it. But we know this 40-bit key is weak, so presumably we could even compute a full key table of about 5 terabytes that would just let us do a lookup. Okay, so we don't know the algorithm. How do we figure it out? Okay, so the first thing we do, sorry, I'm going to skip all this. Just to be clear, if we could do this, if we knew what the algorithm was, the attack would look like this. We would find somebody with a real key. We would scan their key using a portable scanner that we built into a briefcase. We would send in a challenge X that we generated. We would see the response Y that they produced. That's an actual response Y computed with their key. And then we would go ahead and we would brute force the key to try to figure out what the key inside of their immobilizer was, and then we would clone one and build our own. That's the attack we want to run. We can't do that without knowing the algorithm. How do we figure out what the algorithm is? Well, the first thing we do is we go out and we buy some of these things. There's the one the cow swallows, by the way. I'm not sure why the cow swallows it. Okay, so we go out and we buy one. It turns out you can buy an evaluation kit for $400. So we spent some more of RSA's money. It came with this really crappy little reader thing that you could plug into a PC with a serial port, a bunch of different tags, and some really awful software full of spelling mistakes that we basically threw away once we figured out how it worked, and we wrote our own. So the first thing we did, we basically wrote a command line interface that would allow us to set a key in a device and then send in a challenge, a 40-bit challenge, and then get back the response. Now, one of the things that's different about these devices we bought than the Speed Pass or the one in your car is the ones we bought were unlocked. And unlocked means that we could set the key. Obviously, if I could set the key in your Speed Pass, it wouldn't be a very good Speed Pass. I could just set it to something else, or I could do whatever. These guys are unlocked, which means we could actually set the key and do experiments on it. So we did that. We sent in a bunch of challenges, and we were almost there, but we found out we couldn't quite do it because there was a tricky security feature built in. So it turns out every time you send a command to this chip, you send the data, whatever it is you want to send, and there's a CRC at the end of it. CRCs are usually computed with some seed. The problem is this CRC was computed using a secret value. It's a 16-bit CRC, and every single transponder uses the same CRC algorithm. So how do you figure out what a secret 16-bit CRC seed is when you're given a tag to check against? Yeah.
You try all 16.
Yeah.
6,000.
65,000. Right. So we did that. So it turns out this security feature that this comes up later, because later on, after we did the research, we went to TI, and we said to them, like, we did this research, and they said there's no way you could have done this because you did not know the secret seed that's used to calculate the CRC. And we said, oh, is it OX, FED3? And they said, how'd you get that? We said, it took us like a millisecond. We just ran through like 2 to the 16 possible things and checked to see if they were right. Okay, so this is just another lame, bad security feature that they threw into the system. It has nothing to do with the cryptographic key. So we guessed it. It was very easy. Okay. So now we have the ability to program our own 40-bit key into one of the test devices, and we can send it a 40-bit challenge of our choosing, and we can get the 24-bit response back out of it. We did some experiments, and we saw this. The secret code, which is an alternative name for key, is here on the left. We just tried with 0 keys, and we sent in challenges, and we sent in responses. Do you see a pattern that might be emerging here? This doesn't look like a very good cipher, does it? Okay, so our theory is that maybe, let me see, we did a few others. These are all Fs with Ds in different positions. You can see those patterns kind of emerging here again. This is looking kind of worrying, not great. And if you look here, we kind of figured, well, maybe this is actually just a truncation of the input. Looks kind of bad, doesn't look great. So we hypothesized that maybe all this cipher is doing, at least when you set a 0 key, is chopping off 16 bits of the input. Not good, looks pretty bad. But it wasn't consistent. When we set other keys, it did some stuff that was very different. And then we got lucky. We got very lucky in that somewhere on the internet, one of our fellow grad students who was Googling very hard found this. And we thought, oh, this is done. We now have the algorithm. It turned out there was a presentation by a doctor, a researcher at TI, a guy named Dr. Ulrich Kaiser in TI Germany. And he said, the current Texas Instruments algorithm sucks. We need to replace it. By the way, here's a picture of it. We thought, awesome, great, we have the algorithm. Okay, it turns out this is actually, and I'll show you a little bit about this, it's a hardware cipher. It's a very common design. You have a 40-bit input register up here. That's the plain text. Down here, you have a 40-bit encryption key register. And this is wired, so bits of these key go through this routing network, whatever that is, we don't have the details, and go into these boxes that are called these F boxes, right? Kind of looks like we've seen S boxes, so F boxes we'll call these. The outputs of each of the F boxes go into another set of 4 F boxes, 17 through 20. The outputs of that go into this F21, and 1 bit pops out of the F21 box, comes around here, and gets pushed into the left side of this register. So presumably what you do is you put in your plain text here, your key here, and then on each cycle, and it says there are 400 clock cycles, and it's 40 bits long, so that would work out to be 10 rounds. So for 400 cranks, you get a new bit on the left side, your plain text gets pushed out, and something happens that presumably munges up whatever is in the challenge register. You can see there's also a key update schedule down here. The documentation says this happens every 3rd clock. And basically it's just a linear feedback shift register. You're taking 4 bits out of the key, XORing them together in a simple linear function, and sticking this back here on the left side. Okay, so this is the entire algorithm. Seems good. Seems like we're done, but we're not done. We're not done for a bunch of reasons. The first one is we don't know what's in these F boxes. That's really critical. We don't know what's in this routing network. That seems really important. Even if we assume everything, all the details in this are right, we don't have the wiring that actually makes this cipher work. So how do we figure it out? Well, the first thing we did is we came up, sort of accidentally reinvented something called a slide attack. This is an attack that you can use against this kind of shift register-based cipher. Okay, so our idea was this. So what we really want to do is the following. In order to do black box testing, we currently have the ability to put in any plain text we want, any key we want, crank it, and we said go off and do its thing. It cranks for 400 cycles and sends back whatever it gets back in this register, or 24 bits of it. It chops off 16 and gives us 24 bits of it. What we really want to learn, though, is not what happens after 400 cycles. We want to learn what happens after 1 cycle. We want to learn what happens if we put something in here that we chose, something in here that we chose, what bit comes out of F21 after 1 clock cycle. We can't do that. The stupid thing only gives us the output after it's really just turned the crank. It's like, I want to know what happens in a blender after 1 turn of the blender wheel. Unfortunately, all we get is what happens after 400 turns of the blender wheel, which is basically a smoothie. We don't want a smoothie. We want to just know what this blade is doing in 1 bill. Okay, so we came up with a technique to do this. And the idea was this. So what we would do is we would put a chosen challenge of our choosing. We would set the key to something fixed, maybe 0 to make life easy, because that key never updates. We put a chosen challenge of our choosing into the thing. And if you visualize what happens here, what's really going to happen is at each clock cycle, a new bit's going to be pushed onto the left side of this register. And so over time, if you sort of follow what's happening, if you just draw it this way, it's going to, 400 clock cycles later, you're going to end up with whatever the contents of the register are here. And we determined that the outputs, the signature, comes out of the rightmost 24 bits of this register. And so this is just a visualization of what's happening in these 400 clock cycles. Unfortunately, we only control this, and we only see this. So how do we get this bit? Any ideas?
Yeah, you have the resources. You could try and get into the IC and
Yes,
pull it
we
off
could.
there.
Did I mention we're computer scientists? And we have no idea. And during the course of this project, I picked up a chip and put it close enough to my nose that static electricity leaped off my nose and fried it. And I just give this as an example of why we're not going to be like reversing things with electron microscopes. Like, we do not have the skill set. Anything we do has to be done on a computer using black box techniques where we just set stuff and get stuff back. And probably smarter people could have done this, but we did not have the resources. So we had to do it using a black box technique. Okay, so how do we get this next bit? We came up with an experiment. And the experiment, let me see if I can try to explain this in a very simple way. Okay, so what we did is the following. So let's say that our initial challenge is C. Well, what we know is that after 1 clock cycle later, so this is at 0, and 1 clock cycle later, what we're going to have is some bit B, which is what we really want to find out, plus, 39 leftmost bits of C. That's what's going to be there 1 clock cycle later. And our idea was if we could neutralize the encryption key update, just leave that aside, what we could do is we could feed in the following. We could feed in, at time 0, we'd feed in C. And then on the next test, also at time 0, we'd feed in 1 concatenated to 39 bits of C. And we would also run another experiment where we would feed in 0 concatenated with 39 bits of C. And our idea was that if you take the original challenge and feed it forward 400 times, you get to here. You're going to get the actual signature. If we guessed right, if the bit that comes out of F21 is 0, and we feed this challenge in, what we're doing basically is we're feeding this challenge in, what would be the second stage of this processing, but we're now feeding it in at time 0. And so what's really going to happen is we're going to get a result that is exactly 1 clock cycle, the equivalent of the 401st clock cycle passed when we started, when the original challenge started. If we guessed B right, we would get essentially the same signature as we got in the original test, but just one shifted over. What happens if we guessed B wrong? What if we put in, what if B, when we calculated on C, the actual value would be a 0, but we do an experiment here where we feed in 1. Well, chances are what's going to happen there is the result is going to get really screwed up. Because remember, this thing has this avalanche effect where all of the bits of this challenge register go into those F boxes and are used to determine the next bit that comes out. So if you put in the wrong challenge, it's very, very unlikely we're going to get a result that is related to what we wanted. And this thing is called a slide attack. It happens on all of these ciphers. And you can use this to isolate components and different pieces of what's going on inside. So we ran the experiment. We fed in a bunch of challenges. We ran it all night long. A bunch of challenges and our guess for what the next one would be. And none of them worked. Our whole idea was bunk. Nothing came out looking the way it should look. And so out of desperation, we decided that maybe Dr. Ulrich Kaiser was a liar. And that maybe this was mostly right, but he had obfuscated a few details of this just to screw with us. And so in the last desperate test, we said, well, maybe F21 doesn't put out 1 bit. Maybe it puts out 2 bits. It was just a wild guess. And so we tried our experiment again. This time, we put in 0, 0, and 0, 1, and 1, 0, and 1, 1. We had 4 tests for everything. And it turns out that experiment produced results that made sense. So we were able to update our diagram from F21 putting out 1 to F21 putting out 2 bits and sticking them over here on the left side. It doesn't run for 400 cycles, it runs for 200 cycles, but producing 2 bits in each cycle. Great, this is fantastic. We also, with a little more experimentation, figured out that the key schedule Dr. Kaiser had given us was not right. We had to change it a little bit, but it wasn't very interesting, so we just updated it. And as a result of that, we now had the actual cipher that was being used. We had the full design, which is really cool. No, we didn't have the full design, sorry. We still didn't know what these F boxes were. We had no idea. Just knew that this was going on here. Now, can anyone guess why you would take, well, maybe there's no good answer. Let me show you some statistics. Okay, so that's the fix to the cipher. Then what we started doing was a bunch of tests. And the idea of the test was super simple. Okay, so we talked about the avalanche effect. We talked about the idea that if I encrypt a value C, and then I take C off from C by 1 bit, what is the output going to look like? If I encrypt a value, and then I flip 1 bit of that plaintext, and I encrypt it again using the same key, what should the output of those, how should the outputs of that cipher be related?
Should be very different.
Very different. Good. More specifically. We had a word for this, somebody said. Started with an avalanche effect. Good. The idea of the avalanche effect is that a little difference in the initial conditions can cause a huge change after the cipher runs through all of its operations. So if I run C, by the time, and I run C prime where it's just off by 1 bit, by the time it comes out of the cipher, I should get like half the bit should be different. Should be really trashed. The question we were asking, though, is if you go back to the cipher and you look just at this F21 box in the middle, if we run the experiment once with C and once with C prime with just 1 bit changed, what is the probability that the output of just 1 clock cycle, this box, is going to be different? And so using our new technique where we could isolate the output of F21 after 1 clock cycle, we could now test that and we could run experiments. And what we found is, probably a lot of this is just statistical noise. When we flip the 0th bit, about 20% of the time that box output changed. We flip the first bit, a little bit less, but about the same. Most of the bits, had about a 20% probability of changing the output of F21, which is pretty normal, except for bits 38 and 39. Anytime we changed these two input bits in the plain text register, the output of F21 changed 100% of the time. What does that tell us? Why are those two bits special? Yeah.
They might be wired directly into F21, or there might be some F21 is somehow XOR.
Ah, good, very good. That was our guess too. Our guess, if you are definitely guaranteed to get a different output when you flip either of these bits, then it's actually pretty likely that the output of F21 is not just some like low probability of change function. It probably looks something like this. F21 is calculating on the first 38 bits, but then is XORing its output with 38 bits 38 and bit 39, and that's being used to get this thing. Is it? Now I wonder if anyone can recognize what kind of cipher we're looking at. You've seen this cipher. It's presented in a very different way. Now you remember the DES cipher, right? How does DES work?
It's a Feistel cipher.
Good, and what does a Feistel cipher do?
It takes it basically XORs, well, it puts it into like a function, and then it XORs the input with, I can't remember.
No, you're good. But so we split the input into two halves. That's the key step. We take L and R. Let's call this the leftmost, I don't know, 20 bits, the rightmost 20 bits. And you're absolutely right. We take one side and we feed it to some function F with a key. We take the output of that function and we XOR with R. And that gives us, this is one round of the function. Obviously, we don't stop after one round, but we keep going. And this gives us, R prime, and then we take L and we just go on and we just keep doing this. Okay. Now, what if I did the following? Right, in DES, we took our 56-bit or 64-bit input and we split it in half. What if we don't split it in half? What if we keep this basic Feistel design, but we make this split be 38 bits on the left side, 2 bits on the right side? It's crazy looking, I know. It's still a Feistel cipher. It's called an unbalanced Feistel cipher. So we take our 38 bits, and we feed them into this magical function F, which is actually composed of all these little F boxes. We take the output of that, and we XOR it. Oops, sorry about my wires here. And it comes in the other side. My mistake. I should probably draw this a little better. And we XOR it, and then we stick it in here. And we, take, anyway, just forget my drawing. It's not very good. But basically, it's a Feistel cipher. And of course, doing it one round doesn't do you squat because you only get 2 bits enciphered per round. But if you do it 200 times, then what's going to happen is the original input's going to be pushed out, and over time you're going to get a real encipherment as long as these F boxes are actually doing something good. Does that all make sense? Okay, so this is an unbalanced Feistel cipher. There's one other example of a very common, well-used unbalanced Feistel cipher, which is skipjack. I mentioned was used in the Clipper algorithm, but basically in the Clipper chip. So basically, unbalanced Feistel ciphers exist, and this is clearly one. Now let me ask you, why would you use a block cipher? This is clearly a block cipher. This thing is not encrypting anything. It's basically, what is the primitive that we would want to use? If you had to design this whole thing, this challenge response protocol yourself today using modern cryptographic primitives, what would you use? What are we doing? Somebody else.
Use a stream cipher?
Well, we're not encrypting anything. Why would you use a stream cipher?
Hash function.
I like, you're getting closer. You're very close to what we actually want, but you're just one off.
Pseudo-random functions?
That would work, but I'm still looking for something different. Mac. Good. This is basically a Mac. What we're really trying to do, if we actually look for the primitive we wanted, right, we would have a Mac key. And why a Mac? Well, the definition, the security of a Mac comes down to you can't forge a Mac for an unknown message unless you know the key. And so Mac is really what we want to build, but they're not using a Mac, they're using a block cipher. Statistically, if you were to look at this, what's good about a block cipher? Can anyone think of any reason? Just put yourself in the heads of the engineers at TI.
They're cheap as far as complexity goes. Like,
Okay.
They're not all that complicated, and they're pretty fast.
Okay, sounds good. What else? What else statistically works better? Why not use SHA? Why not use MD5? I mean, clearly because you're cheap, right? But what else, what about this has some nice features?
Collision.
Good. So statistically speaking, a block cipher is a permutation, which means that if you built a bad cipher, bad hash function, you could have lots of challenges mapped to the same output. Now, that might be bad since they're so short. With a block cipher, you're truncating, you're throwing away 16 bits, but you're guaranteed to get like a nice statistical distribution of challenges to responses. They're going to be pretty smooth. They're not going to be all clustered or clumped or anything like that. So that's probably the reason. Okay, so I'll try to cut through some of this. We still have questions. What's in these F boxes? What's in these routing networks? And it turns out this part gets a little detailed and boring, so I'm going to skip past most of it. But it turns out that we got very lucky. We found another set of experiments we were able to run that started to tell us how these things were wired together. And what we realized was that these yellow boxes were connected to this yellow box up here, and these blue boxes were connected to this second box, green, and so on. It's a very predictable wiring pattern, nice and helpful. And it turns out, once you figured that out, you could just try to guess that the key does exactly the same wiring. So that tells us how the routing network works, or at least parts of it, so that's very helpful. And once you have that information, we can start to actually drill down to the individual little F boxes just by doing statistical tests, all by putting in a ciphertext, flipping things, and seeing what the probability something changes is. And by looking at the differences in probability, we can start to identify which boxes are wired to what. And we get this really complicated, hard to predict wiring pattern. Thanks, TI, for making it really easy for us. And it looks like this. Okay, and so it just keeps going. And once you've figured out a few of these, you can pretty much guess that the rest are going to repeat. So this routing network and all these wirings are not very complicated once you know this detail. And so now we just have a question of what is inside of these boxes. Well, it turns out once you can isolate a single round of output and you can isolate a single box, which we now have the technique to do, you can basically just run a few more tests and you can compute a table that is basically a description of the function that each of these F boxes compute. And we did that, and finally we had a full description of the cipher. We could actually implement the cipher ourselves in software, which we did. And we could do something where we could actually try to guess keys, and all of our guesses worked out. So we have the cipher. This is great. We're done. So we made a software version. We tried to guess a secret key. 40-bit secret keys in this class, I keep telling you, not very strong. There's only about 1 trillion of them. Trillion's a big number. Okay, so we tried this. So we tried to do a brute force attack against our own speed pass. And what we learned is that 1 trillion is actually a pretty big number when it comes to computers. It took us about a month, or it would have taken us about a month to actually brute force through all these things. Okay, so we did this thing. It was not great. We were able to get about 200,000 encryptions per second, even when we optimized. That would mean an average cracking time of 31 days. The good news, as you already know, because I showed you a picture, is that hardware is very fast. For about $200, you can get a commercially available FPGA, and this was a few years ago, so they're probably cheaper now. We were able to, on that hardware, by implementing the same cipher circuit in the HDL, we were able to get this to 16 million encryptions per second. So just to give you an idea of the comparison between these two different techniques. Okay, that took us down to an average of 9 hours. But 9 hours is too long, so we want to speed that up. So we bought a bunch of them. And this is our FPGA cracking rig. And that's actually a keyboard, and you have to type in the key with the keyboard. It was really horrible. And you have to plug everything together and flip dip switches. It was the worst thing ever. But 16 times 16 million encryptions per second, this turns out this key search is embarrassingly parallel, which means you can just break it up into pieces, and everyone could just take their own little chunk. And we got it down to 35 minutes, and if we'd spent more money, we could have done it faster, but this was all of RSA's money that we had, so we were done. Okay? So we got this to 35 minutes on average. Sometimes it took an hour, and we actually found our first keys using it on Christmas Eve. A very simple device. Okay, so we could have done better. If we'd spent more money, we could probably have done better. This was like in the mid-2000s, so at the time, the idea of having 5,000 gigabytes was a lot. But we did do the math, and we realized with some careful storage, we could have just built a pre-computed table. We could have encrypted the plaintext 0, or some fixed plaintext, with every possible 40-bit key. And it would have taken about 5,000 gigabytes. 5,000 gigabytes was like, wow, this would cost us our entire lab budget back then. Nowadays, how much does it cost to buy like a 2 gig drive?
A 5 terabyte drive would be like...
A 2 terabyte, I mean.
2 terabyte drive is like $80.
Yeah, so nowadays this is not too infeasible. Back then it would have been like 15K. Okay, and this would have really improved the lookup time because we could have just done a logarithmic lookup into a disk. Would have been super fast. There's even a better thing, and we haven't talked about this. You can actually get the best of both worlds. There is a thing called a time-memory trade-off. You may have heard the term rainbow tables, and we'll talk about that a little later. Rainbow tables actually kind of combine some storage with some computation, presumably for about $1,000 bucks, or maybe even on an iPhone. You could have gotten this down to about a minute, and you could have made something very portable. You can see what we were working with at the time was pretty crappy, but it could have been a lot better. And you would have been able to actually go out in the field and like totally steal cars. So we had to do some real world testing. So actually, at this point, we figured this is a research project, we're done. We have the cipher design, we verified that it works. There's nothing left to do, let's just tell TI and write a paper about this. So we did that, we called up TI, and we said, this is totally insecure, your cipher is really easy to reverse engineer, like you should fix this. And they said, we don't believe you. And this is one of those things you have to get used to when you do this kind of work, is that the first thing a vendor will say is like, you're lying, like you can't actually do this. They brought up this CRC thing and whatever, they brought up all this stuff. Then they came to our lab in Baltimore, and these were like old school TI guys, they were wearing like green jackets, it was very weird. They came to us and they brought us a bunch of chips. And they said, we don't believe you can do this, can you crack the keys out of this? So we did, and it took us 35 minutes per key, and we gave them the numbers. And so they got a little worried. And then they said, well, the fact that you can do this like in a lab doesn't mean that you can actually like steal cars or steal gas from Exxon. So clearly this is not like a real attack. And they were right. We hadn't actually implemented something where we could go and steal speed pass stuff or steal a car. And that meant we had like 3 more weeks before the paper deadline, so we had to quickly bang something together. So we did. Okay, so we made a portable testing rig. Consisted of a few different pieces. So the first part was just like my old laptop and the radio system that we got from the TI evaluation kit, which we had to be super careful about because TI had now stopped selling evaluation kits as a result of our disclosing this. So we had to make sure we didn't break this. So we built a portable testing rig, and you can't really see it well, but here are 2 people sitting on a couch in a really awkward and totally not posed situation where there's a briefcase in between them. That briefcase has a computer in it, or it has an antenna in it, and the person has a key in their pocket. And what the antenna is doing is it's scanning them and sending out, 0 and getting back a known an encryption of 0 using whatever key is on their chip. We extracted the secret passcodes, 35 minutes, and we cracked a whole bunch of real speed passes and immobilizer chips. And then we had to go do stuff, and this is the part that took forever. So we were trying to defeat immobilizer systems in cars at this point, so we built a device we called the Mobilizer. It's not very mobile. It consists of a bunch of batteries. This is actually just our thing we took to EasyPass, so we just repurposed it. A couple of big batteries for a UPS system, our shuttle box, our analog digital converter. It is not portable. And cost us like, a couple $1,000 bucks, whatever. It's just stuff that we had to buy. And we put it on a cart, and we took it out to do stuff. Okay, I'm going to skip this part. So I have a video. I'm going to see if I can show you. This is the world's most embarrassing video. I hope I have it. If I don't have it, I'm going to let you guys down. Let me see if I can actually show you the video. Does it play, Tisha? Please. Hang on a second. I think I have it here. Come on, computer. There it is. Okay, is there sound here? I'd really like there to be sound, because the sound is awful, but maybe I can make it loud enough that you guys, if you're just very quiet, will be able to hear it.
Sound goes through HDMI.
Oh, sound goes through HDMI, but yeah, I don't know if it'll go through the adapter.
It's good.
They all have them. Keychain cards.
This is a very
membership
embarrassing
cards,
local news
speed passes.
video.
They're high-tech trinkets that are supposed to make our lives easier. But we found if you're
The first
not
half has
careful,
nothing to do with
they
it.
could get you into deep trouble. It looks so innocent. 2 people walking past each other. But watch. Did you see it? Stole her identity. How? By lifting the information stored on her keychain. So we'll take a look at these customer cards to show you how he did it, and if there's any way to protect yourself in the age of high-tech shopping.
Giant and Super Fresh and library card, CVS.
Like so many shoppers today, Karma Quinn has more cards than keys on her keychain. But do you know what's on those cards?
I really never even thought about it. No, I never have asked.
This part is kind of...
I guess whatever I buy.
Safeway says it does use the cards to keep track of what discounts bring you into the store.
There is no billing information attached to your card. So your card really is just meant for discounts and specials that you receive.
So if you lose a keychain card, like this one we found laying in a parking lot, a thief couldn't charge groceries on it. And you need a scanner device to read what little information the cards do contain, like your name and address.
You can tell if it's a scanner card by looking for a barcode, but you won't find a barcode on a mobile speed pass. That's because there's a tiny little radio antenna embedded into the device, and that sends all of your information to a computer inside the gas pump.
Or right into the hands of Green. Luckily, Green is not University, whose team managed to break into this supposedly unbreakable technology. To show us how they did it, we asked our intern Catherine to put our Channel 2 speed pass in her purse. Watch as Green walks past her. Use radio signal right now. You missed it, didn't you? Hidden inside Green's bag is an antenna which intercepted the keychain's radio signal and sent it to his laptop computer.
All we have to do, really, is wave the speed pass somewhere near this antenna, and all of the information, which is these numbers here, everything we need to make a copy of the speed pass comes right up on the screen and gets recorded. So she doesn't even know that we got this information. As far as she knows, I just walked by her with a briefcase.
Green says it takes less than half a second, and he could steal hundreds of codes by walking through a crowded place like the airport. Now armed with our account information, our would-be identity thieves go on a shopping spree. First, they trick the pump into giving them gas with our stolen account number.
We can buy as much gas now as we can fit in the car. Might as well get the best stuff.
Now, with a full tank, they take their free ride even farther. Their fake speed pass is tethered to a computer in the car. They say it would be easy to build a portable version, but they haven't needed to. Because the cord didn't stop them from buying as much junk food as they could carry.
Do you have a plastic bag for any chance?
With our stolen account. In a written statement, ExxonMobil told us no fraudulent purchases have ever been made with a cloned SpeedPass device. We strongly believe that the SpeedPass devices remain much more secure than those made with credit cards. ExxonMobil also pointed out that the guys from Johns Hopkins are very, very smart.
I'm sure your mother is proud.
Here at Johns Hopkins are very bright, and we're able to do this in a short amount of time, but people shouldn't be naive about this. You know, organized crime has a lot of resources, they have deep pockets, and when there's a way to get around the system, you know, the bad elements in our society figure out a way to do it.
Professor Rubin says the invisible antennas used in a speed pass could soon be used in passports, the European euro, even Michelin tires. So your information and your whereabouts can be tracked everywhere you go. And that bothers Matt Green, who knows better than anyone how that information can fall into the wrong hands.
Even when it's sitting in your pocket, it's broadcasting all of your information out for anybody to see it, to pick it up who has an antenna. And I definitely don't use speed pass anymore.
Makes you think twice, doesn't it?
I only kept it on just for that last one. Okay, so yeah, I mean that's you know, these things the news coverage is a little ridiculous. Nonetheless, you know, this stuff was actually kind of a problem for their system because they really did have billions of dollars of cars. I'm just going to pop up one or two more quick things. How do I get back to slideshow mode?
Guys at Johns Hopkins are very smart.
Go. So I mean oh god really. So the two lessons here, first of all, is this is a case where, you know, security through obscurity and Kirchhoff's principle really matter. You don't want to be securing your stuff using proprietary algorithms because people can't actually figure these out. We can build a device that does the whole process, and we could actually, you know, copy a bunch of people's stuff and do it directly. And I think there was one other thing. So what are the fixes for this? That's what I wanted to get to. How do you fix something like this? It's hardware. It's in everyone's pocket. What do you do to fix it? There's not much you can do. We found that tinfoil was pretty effective. You could wrap your keys in tinfoil and it would actually work. There wasn't much that people could do. However, and this is the part that I want to show you, eventually TI came up with a fix. And the fix, of course, was not to use standard encryption algorithms, which is what they should have done. The fix was, let me see if I can get this. It is called the DST plus. And the DST plus, instead of having one instance of the DST cipher, which you've already shown is 40 bits, has two instances and does mutual authentication between the two instances so that you can't query the thing unless you actually know its key. Is the DST plus secure? I will leave that for a potential future exam or homework question because it's a really fun thing to look at. And that's it. So I'm going to let you guys go and we can pick up. I keep promising you a reading list. I'm going to send you a reading list, but I figured I'd let you get the assignment done. And projects, please write me with projects that you are going to do. We need to pick them. Yes?
So I've seen something similar to what you did, but with credit cards.
Yeah.
Is that like the same idea?
This depends. Probably different algorithms, probably different systems, but people have done things like this for a couple of different hardware.
Does that also work if you have the chips?
Yes, it does. Some of these credit cards have contactless systems, and they're very broken. Yeah. Projects, people, pick projects. Let me know soon. Pick your team because we need to actually pick these and get moving.